and let me introduce the next one, Dongmei, Xiao. Okay, Dongmei, Xiao cycles bifurcating from a period annulus.
Okay, thank you. First of all, I would like to thank the organizer committee for giving me the chance to present our work. This work is based on the joint works with the Jean-Pierre Francois. He is a professor in Paris 6.
Okay.
Our talk, we divided 4 parts. First part, we give some the background, and the second part, this is our second part. Third part is our work, and last we give some of the discussion. And as I think everybody knows, in 1900, Herbert in the second SM proposed the 23rd problem, and the Herbert 16 problem is open up to now. And this problem divided 2 parts. One is the first part is to ask the relative position of the closed and separate bridges for a planned algebraic curves of the nth odd when this curve has the maximum number m of the closed and the separate bridge. And this part, the great mathematician Pетровskому made a great contribution on this problem. This I find his paper, this one. And the second part is to ask the polynomial, planar polynomial differential equation of the degree n, how many nimicycles, this is the second part. And also the great mathematicians, Leaders and Portrait made the great contribution for the second part. And today we talk about the Herbert 16 problem on the period annulus. What means the period annulus? We said a planary polynomial vector field has a family of the period orbits. This family period orbits consists of the period annulus. With, for example, we say this is a planary vector field has a family period orbits, which can homomorphize to the standard annulus as one time this interval. So if we consider this unfolding of this function x, this vector field x0, we can choose a global transversal cross section to x0, and this unfolding with the capital N number of the parameters. So we can define the Pancreas map, or we say this first return map. For this return map, we can study this map and find some isolated fixed points, and you can get the nimicycles, because this is one-to-one correspondence with this kind of isolated fixed points. So if we define this Pancreas map minus identity map, we can say this is a displacement function. if we study the displacement function, we look for the isolated zero. This corresponding to the limit cycles. So today we talk about the hypothesis problem is to study the displacement function, how many isolate zero for this function. If the displacement function is an analytic convergence series with the coefficient fk of parameters lambda, so we can give the exponential like this way. This function, the coefficient are polynomial. So we call this polynomial the derivative, the displaced function, the derivative is called the manifold function of order, for example, order 1 or order 2. And one question is how to understand the geometry of the analytic hypothesis as defined on this cover. And another is the center set. C is the affine algebra set defined as the zero set generated by all the coefficients fk in the Loden round. We also call this is a Gaussian idea, this coefficient fk. So up to now, the hypothesis 16 problem on the period annulus is also a big open problem. The Professor Gablov in France made an assumption. He said if this the cyclicity of this period annulus under this final condition, he proved there exists an analytic arc such that the equality hold. That means for the general case, we consider the number capital N parameters perturbation. Now you can choose one small perturbation, one parameter, epsilon. This is one curve. You got this maximum limit cycles, this theorem. So we decided this arc epsilon to lambda bar epsilon maximum the cyclicity. This now next we talk about this arcs. But for his work, don't answer these two questions. One, the theorem just prove there exist the arcs, but don't tell you how to construct this exponentiality family of the arcs, maximum the cyclicity. This is one question. Another is this we talk about the manifold function of order k. This k is the first. That this manifold function is not a zero function. Another question is this k is finite or not. So this question is, does there exist a finite integral k star such that the k star of the derivative of the display function is not a zero function? That means k star of the manifold function is not zero function. So you can use this k star of the many function to get the manifold the zeros, the number of zeros of the k star of the many function to get the limit cycle number. So usually we call the case study is called the essential order or called the Iliad number because the Iliad first considered this problem. And this perturbation usually we call the essential perturbation. Is essential perturbation because this perturbation can realize the maximum cyclicity with the minimum number of parameters. So last year, the Jean-Pierre Francois and Gabriel and I give these two results. One, we proved the Iliad number case study is finite. Another, we said if you know the bounding idea, then you can construct the arc to apply to realize the maximum number of the limit cycle. So for any perturbation of a center, the principal bifurcation function is a linear combination of the factors of the bounding ideas. And their coefficients are the polynomial associated with the Nash K-jet of arcs of the center set. So you can calculate the Nash K-jet of arcs, can get the arc, the one parameter arcs. And this is, we talk about the Heft problem on the parallel orbit, parallel annulus. And another is the weakened Heft 16 problem proposed by Arnold in 1977. He considered this Hamiltonian system plus the small perturbation. And if epsilon equals 0, this Hamiltonian system has a center. So you can get the period annulus. So if we let the gamma h be a closed orbit around the center, you can define the Poincare map pH epsilon this way. And the displaced function dh is pH epsilon minus h. If the k, if there exists the k such that the mk of h is not identity 0, so we call the mk is called the case or the manifold function, or also the bifurcation function of the system. And Arnold, this is perturbation, you get the display function. So Arnold, the problem is to give a bound on a number of isolated zeros of the first order manifold function. So that means k equal 1. We also call this kind of function is R-bar integral because this manifold function and the perturbation are polynomial. This is we call the weakened Heft 16 problem. And another problem we said Arnold Heft 16 problem is that if you consider the Hamiltonian plus small perturbation, and you get the first non-vanish manifold function, this k is not 0, not 1, maybe second, maybe 2, maybe 3. For any k, you can give the isolated, the number of the isolated 0 of this kind of manifold function, mk of h. So my talk will answer this problem for a special Hamiltonian function. And about the higher order manifold function, the computation of the higher order manifold function, there have lots of the works. We just list some of them. The first paper is 指分章. She is my supervisor, and she got her PhD in the Moscow State University in 1955. I'm not exactly, that's the period. And another is Jean-Pierre Francois and others. So for this kind, this paper and studied how to calculate higher order manifold function. But this problem is still challenged to give the equipotentiality bounded on the number of the isolated zero of any order k, the manifold function. So to our knowledge, there are few works about this kind of problem. And the first work is Iliev. He studied the Hamiltonian function is this way. So for this Hamiltonian system, the center is a linear center. Another work is the Borska Libre in the Spain. They studied this kind of Hamiltonian function, x squared plus y squared power m greater than 2. So this also homogeneous polynomial. And this center is global center. It's a global center. So our question is how to characterize the quasi homogeneous polynomial Hamiltonian system have a global center. And another is give a equipotentiality bounded of isolated zeros of a manifold function for any perturbation of the quasi homogeneous polynomial Hamiltonian system with a center. So we first to give the necessary and the sufficient condition for the quotient homogeneous polynomial Hamiltonian system has have a center. So let's recall what means the quotient homogeneous polynomial. We said that a function h of xy is called S1, S2 quotient homogeneous with the weight degree m if we use lambda S1 power S1 x instead x and the lambda power S2 y instead y, you get h, this capital H function equal this lambda m power times h. We call this function h is quotient homogeneous. And S1, S2, we call the weight exponent, and m is called the weight degree. So if S1 equal S2, then the function is homogeneous with the degree m. If S1 is not equal S2, we can assume S1, S2 are combined and one is less than another one. So we give this theorem. If the function h, capital H xy is an S1, S2 quotient homogeneous polynomial of weight degree m, then the Hamiltonian system has a center at the origin if and only if the following condition hold. And y is S1 times S2 divided m. So m divided by S1, S2, you can get the integral. Another second condition is you use the x power is 1 over S2 and y power 1 over S1. Get the function, new function h star xy. this new function is a homogeneous polynomial. Degree is this integral. And the third condition is this homogeneous function, a homogeneous polynomial H star has no real linear factors. So that means this function, if you have the factor, this factor must be irreducible homogeneous polynomial of degree even. So this is a necessary and sufficient condition for this function has a center. So if this condition, the three conditions are satisfied, then this Hamiltonian system has a center. This center must be global. If it exists, then the center is global. So we can assume this period annulus is gamma h. This h greater than 0, less than positive infinity. This theorem, from this theorem, you can get easy corollary. If the function h is a homogeneous polynomial of degree m, then the system 1.5 has a center at the origin, if and only if this function has no real linear factors. So this is easy to judge it. This origin is a center or not. So this theorem proof is based on three propositions and some results in the Weiguli and another results. So this due to the limited time, I didn't give the detail about this one. Next, we talk about the boundary on the number of zero of the manifold function of Quantum homogeneous Hamiltonian system at any order. So we divided the two parts. One is a homogeneous Hamiltonian system, the small perturbation. Another is the quantum homogeneous Hamiltonian system. For the small perturbation of a homogeneous Hamiltonian system with a center, we can write this system one in the one form this way. So the equation can write down this one. And this is Euler vector field because H is a homogeneous, so degree is m. So use this Euler vector field, put this function, you get this function equal mh. So follow the math, the first one, we can define the like the Pangolin map and got the display function. And we can say any analytic one form omega can be written in the form omega equal to 1 dh plus df1. So this is a multi-value analytic function in this way. So for this one, if we would use the algebra of the successive derivative, we should to say this function, the Hamiltonian satisfied the star property with this the period annulus. So what means the star property? The star property is that for any polynomial one form omega, such that this one form integral along this closed orbit gamma h equals 0, then the omega must be can write down this way, equal g d capital H plus D capital R must be can read down this way. So for the homogeneous Hamiltonian system, we can say, we can check this star property satisfied. So for the, now we calculate this first manifold function. M1H equal omega gamma H. This omega is any perturbation. The polynomial perturbation P xy and Qxy are polynomial of the degree n and the degree n. So you can write down this way. So this, if homogeneous, we can find, we can use the variable, the change of the variable, like this way. We can fix this orbits gamma H onto gamma 1. So that is care stamp. We can do this one because we can use this kind of variable change, can get the all gamma H to gamma 1. So use this one, we can say the first the manifold function M1H, the number of this one is less or equal than n plus 1. If M1H identity 0, we can calculate order, the higher order manifold function. The M2H, the number is at most 2 times n plus 1. And so we can get the K manifold function has at most K times n plus 1 isolated 0. So this proof, we just use the inductor. So next we said if Queen's homogeneous Hamiltonian system, the small perturbation, how to get the bounded of the isolate, the number of the isolate. For this one, we can use the P xy and the Qxy, the exponential, according to the Queen's homogeneous way to exponential. So this one, this P and Q is not Queen's homogeneous. So we should exponential according to the Queen's homogeneous way to exponential. So like this one. So we get this theorem is if this capital H xy is homogeneous, is Queen's homogeneous, and we can, the first non-zero case, all the manifold function mk of H can be expressed as this way. And this coefficient AI is a constant. If base I is even and S1 plus S2 is odd, the AI is 0. So from this expressions, we can get the isolated numbers. The MK has at most the capital K isolated zeros on this interval. This capital K equal this one. If the number n and the K S1, S2 satisfy this condition, the number is this way. If K and S1, S2 is this, satisfy this condition, you get the number is this way. Another is this way. And we use this theorem, we can improve the homogeneous case. You can get the number is less than the first part we get. So for the homogeneous case, this case manifold function has as at most K times n minus 1 over 2 take the maximum integral part, 0 if k is odd. If k is even, you get this one. The theorem proof, we use some the lemma. We don't give the detail for that. Last, we said the upper bounded k in the theorem 30, the theorem 3.6 are not optimal. Usually, we give an example to show this way. This is a Hamiltonian, but it's a quasi-homogeneous function. We put the perturbation. This is a polynomial of the degree 2. We can calculate this M1. M1H has no zeros. M1H. If M1H equals 0, we can calculate M2H has at most 3 zeros. But if we use our formula, we get M1H less than 2. But for this is just the 0, that is 0. And the M2 use our formula, this is also 3. If M1H identity 0, the 3 is optimal upper bounded. If M1, M2 identity 0, we can get M3 has at most 2 0. And this 2 is also optimal. So this showed our theorem the upper bounded is not optimal usually. So left problem is the bounded on the number 0 of manifold function at any order for general Hamiltonian have a global center. This is very difficult for this case. We cannot fix the any closed orbits on the one fixed on one closed orbits. So from this one, we can solve some of the center focus problem. We don't know. That's the left problem. Thank you very much, and Happy New Year to all of you. Thank you. Hello.
Okay, thank you very much. It was very detailed talk. And maybe somebody has questions, you are welcome. Of course, no Russian, only English. Yes, here.
Извините, вот такой вопрос. Известно ли вам что-нибудь по классической постановке? По классической постановке 16-й проблемы. То есть, когда у вас многочлен второй степени. Обычно бывает так. Когда я могу ничего сказать, и когда условия изменять, когда хотя бы что-то могу сказать. Спасибо.
Sorry,
English.
I cannot hear you clearly.
Yes, Professor asked you about the classical formulation of 16th Hilbert problem. Can you show it once more, the classical formulation? When you have the 2 degrees polynomial at the left-hand side.
Which page?
He asked about the classical, a classical 16 Hilbert problem. Classical position, when you have the polynomial at the right-hand side of your system.
Polynomial system.
Polynomial system, it is the beginning of your talk, I think, when you formulated the Hilbert problem. Not here, but before.
Before
Before.
this one,
The first one, maybe.
first one,
First page.
first page, first
Mhm.
page. Okay.
Oh, correspond. Yes, yes, yes. Oh, yes, this system. And when F and G are the 2-degree polynomials.
Yeah, quantic polynomial.
Yes. When M
Yeah.
and N equal to 2.
Yeah, yes.
And what is the formulation of 16th Hilbert problem?
Yeah, for the quadratic system,
Yes, what is the
up
question?
to now, we know this, up to now, the number is 4. The number is 4. But we cannot know this 4 is whether or not is the least upper bounded. The Chinese, there are 2 groups. Give the 2 examples to show the quadratic system has 4 limit cycles.
Okay, thank you very much. Other questions, please.
Yes, thank you. Thank you very much.
Yes, somebody would like to ask you. You are welcome.
Yeah, we hope the epidemic is over. Next year we can go to St. Petersburg to attend the SM.
Okay.
Thank you very much.
No
Bye-bye.
questions. Thank you very much. Bye.